Yep, right side, yep. Ah, I see, okay. Okay. Right. Ah, okay. Yeah, so you start needing to... Great. Okay, so let's reconverge. It's 11:15. And so what we'll address now is what is topology, what are topological spaces, how to build them, and how to understand what, in fact, make a selection about which one you want. So context, here is where we are in the discussion. So lecture 2, that's this lecture, this big blue region here. We tackle the different kinds of topological spaces that could be used, various relative merits of them that we may wish to use. Why might I wish to use a CW complex or a topological space generally or whatnot? We'll fit that in. So what do we want to address this lecture? First of all, what is a topological space? What different kinds are there? There's lots. And then how to effectively represent topological spaces or choose the right representation of topological space for your data problem. And in particular, we're going to zero in on simplicial complexes because they seem to be a happy medium between being sufficiently expressive and easy enough to work with combinatorially. I'll put this right out that they're not necessarily optimal in all cases. Sometimes you want something that is not a simplicial complex. And we'll see some of those, and we'll talk about some of the variants there. And then talk specifically about how to encode specific kinds of data as examples. Okay, so of course, as I've said before, what is topology? It is the study of large perturbations or spaces under continuous deformations is the precise term. Large perturbations is sort of the intuitive point of view, which is to say, I'm allowed to make a big change so long as I don't rip or tear on space in some fashion. In that case, then a coffee cup looks very much like a donut. Because in particular, they are both, well, let's see, they're solid. They've got one hole in it in some fashion. They've got a two-dimensional boundary. These are all sorts of features that come out of the topology. Now, in some contexts, you might even say that the deformation I'm going to allow allows me to collapse, in which case this thing looks very much like a one-dimensional object. By collapsing axially this object, so I end up with just a circle. That could be a possible deformation that you may permit, depending on the context. That's called a homotopy as opposed to a homeomorphism. A little more rigid. Okay, so, all right, so what are the different kinds of things that we can talk about? First of all, we're talking about topology, not topography. Everyone makes fun of topologists saying, well, you're a bunch of map makers. Well, we make maps, continuous functions, but not maps like this. I mean, this is a very nice map, but this is very much geometric. What matters here is distance. Distances between things. Topology is less about distances and more about neighborhoods. What's nearby some other points, rather than specifically how far do I have to go. This is how you get the robustness. Okay, so we just looked at this.
Might also be worth mentioning to make fun of the network scientists. You seem to think that network layout is also topology.
That's true. That's true. I don't want to make fun of too many people at this point because it will come back to me.
But there might be a lot of people in this room in particular
Sure.
who come across as the use in that context.
Sure. So I will draw this out actually as an important point of view, that if you talk about a communications network, typically what you'll say when you say network topology is you're saying which nodes are connected to which other nodes. In some sense, that's a one-dimensional kind of thing that is basically looking at the connection graph. What we're really interested in is higher dimensional structure as well, so looking at cliques as well as graphs. The benefit of this is that it gives you some more structure that you can play with and a bit more robustness. But you're right, Cliff, that it is important that is a term that is used, and used reasonably. But we kind of play off of the fact that we're more general. Okay, so we just looked at this data set in the interactive session, and for the benefit of those watching online, this particular data set shows a topological feature where I have, in particular, a loop where I collected wireless access points, as in the listing of the wireless access points through time and their associated signal strengths. As I walked around on this loop, and I personally did this, collected this data, and with that data, if you look at the first two principal components, or even a random projection theorem, most of the time that works, you can see topological features, like, for instance, this loop here. This solid line is just notional. I sketched it in there to highlight it. And if I change the topology, the overall connectedness of this loop, so now it turns into has a self-intersection, so it turns into a figure 8, that's reflected in the data as well. So these are topological features that we'd like to see. We want to see some topological spaces. Now, the nice thing about topological spaces is that there's lots to choose from. This is also a detriment. There are lots to choose from. Which one should you pick? Well, on one hand, if I'm talking topological spaces, maybe I should talk about a general topological space. The name suggests it's general. The disadvantage is, well, it admits a lot of pathological cases that are hard to work with. Things like Cantor sets and worse. Not so good to work with. On the other hand, there are spaces that are very restricted, like manifolds. These are spaces you can do calculus on. Everyone knows and loves calculus. Calculus is great. Good, strong theorems exist. Problem is, there's a lot of data in the world that's not a manifold. I'll give you an example. This one. This is not a manifold. This self-intersection, this ramification point here, makes it not a manifold. So working with manifolds is restrictive, and perhaps too much so. So we want some sort of happy medium, which is a cellular space, a space that kind of, roughly speaking, is I take a bunch of manifold-looking pieces and I stick them together, glue them together on their boundary in some fashion. So less general than topological space, but more general than manifolds, kind of expressive, got some constraints. And if you do them right, they're combinatorial objects that are good for computation. You do algorithmic computation. So that's good. Okay, now, if I am being honest, there are a lot more spaces in the world. There are an awful lot. Here's a is an ISA, so a stratified manifold is a topological space. A manifold is a stratified manifold. Abstract simplicial complex is an undirected graph. And the dotted lines say that I could transform one into the other. This line here is the boundary between what you might say is combinatorics and topology. So everything over here is a topological space. Everything over here is some kind of discrete combinatorial object. And there are ways to go between them. So this is where you can do computation. This is where you can do topology. And part of the reason why topology is kind of hard from an algorithmic standpoint is that most of these sort of things, especially down in this region here, are kind of hard to work with algorithmically. So you want to push as much of your data as you can over to here to work with it. So for the purposes of our discussions here in this tutorial, we're going to basically work with the stuff that's combinatorial. Work with abstract simplicial complexes, flag complexes, hypergraphs of various sorts. And occasionally, when we need to, we'll push it over in the topological space realm. So that's good. Now, okay, that's all well and good. So what do these things look like? Let me give you some high-level intuition first, and we'll delve into some of the precise details. Okay, so first of all, we've got a bunch of points. You can think of these as measurements. Like we saw, this is a timestamp with a bunch of wireless access points, or this is a protein in a protein-protein interaction network, or this is a particular organization in an economic network. So I'm saying it represents a measurement. And remember what I said, for me, a measurement is anything that is a piece of data. Okay, so a simplicial complex is then a collection of these vertices and some other stuff. Well, a bunch of edges, which are pairs of vertices. Sometimes we think of them as ordered. Sometimes we don't. Ordered turns out to be a little more convenient for doing certain kinds of computations. Sometimes unordered makes more sense. This is a graph. Lots of people call this thing a graph. I'll call it a graph. So this is a one-dimensional object. By dimension, I mean the number of elements in this kind of set, minus 1. Okay, but I also permit higher dimensional things, like to glue in a two-dimensional face. The two-dimensional face is going to have 3 things in the list representing it. So for instance, this vertex 1, vertex 2, vertex 3. And in essence, these kind of things are multi-way interactions, telling you that these particular data sources should be checked for consistency 3 ways, mutually checked for some kind of mutual information. Now, terminology, we'll call each and every one of these kind of objects a simplex. The whole thing is a simplicial complex. And if I wish to compare a simplex to the lower dimensional simplices that are subsets of it, they call them faces. So for instance, V1, V3 is a face of V1, V2, V3. Okay, now this is kind of abstract, so let me give you some more concrete examples of this sort of thing. So let me draw something on the board here. So if I have a database, it has a bunch of columns. So if I have a database with a bunch of tables and columns and keys, one way that I might think of these vertices is think of each table is a vertex. And each edge is telling me something about, is telling me shared keys or shared columns. So if I have a table over here and I have another table over here, they each have a bunch of columns and a bunch of rows. And say, for instance, I have here color, shape, timestamp, and size. And over here, I've got timestamp, color, age, and something else. I don't know, something else. Free-form text, maybe. The fact that I have some commonality between these two things, the fact that I have color in common, and the fact that I have timestamp in common, indicates that if I'm going to be comparing information from these two tables, that I ought to be thinking of them pairwise. So if I think about this from a construction standpoint, I've got a vertex here for this table 1, and I have another vertex here for table 2. And the fact that I'm sharing an edge says that, or I'm sharing these two columns is in fact, what is it? It's a subtable. It's a common subtable. So this is a common subtable, and what does it look like? Well, it looks like a table that has just 2 columns, color and timestamp. So you can think of this purely from a database standpoint, or you can think of it from this sort of sense or distance standpoint. There are many different ways to abstractly play with this, but this allows you to get at many different kinds of data. So what if I don't have all the faces? Maybe I don't have this face here, but I do have this simplex here. The result is not a simplicial complex. Simplicial complexes require all of their faces. This thing is then just a hypergraph. Now, terminology-wise, if we've got a hypergraph that's really a hypergraph and not an abstract simplicial complex, usually we'll call these things, rather than simplices, we'll call them hyperedges. Just to be clear that we're dealing with the constraint being that I may not have all my faces, but that's okay. And so sometimes these things turn out to be very useful. Okay, so one of the other things that we might play with, here's another kind of data structure, is a flag complex. So a flag complex is one in which I've got all cliques are simplices. Converse may not be true in an abstract simplicial complex. Here is a abstract simplicial complex. It's a graph. But it is not true that all cliques are simplices, because in particular, this clique here of these three vertices is not present in the diagram. It's present in this diagram. Now, it's worth noting that if you deal with just a graph, you start with a graph, and this is to Cliff's point. If you start with a graph and you have no further structure, it's often quite useful and quite valuable to look at the flag complex over that graph, to ask for all of the cliques and put them in. Reason being is that with this higher dimensional structure here, what does that do for you? That allows you to avoid looking at certain loops that you may not wish to look at. Maybe it's important, maybe it's not. This is one of those things that you need to interpret in the context of your data. But the point being that if you look at flag complexes, there are strong theorems that allow you to manipulate the data in a reasonable fashion. And so it's worth noting that you make the distinction between a clique complex and a non-clique complex, or a flag complex and a non-flag complex. Clique complex is a synonym for flag complex. That sometimes that gives you additional structure that you may wish to know. Of course, on the other hand, it's not like you're adding in any information per se. It's exactly the same information presented in a slightly different format. Okay, so let me now be a little bit more precise about this, give you a little bit of zoom in on this diagram. So these were the spaces that we were just looking at, flag complexes. All cliques are simplices. An undirected graph is just vertices and edges. Both of them are abstract simplicial complexes, and if I don't have an abstract simplicial complex, then I have just a hypergraph. It turns out computationally, it's a little easier to work with invariance of these guys than these guys. So above the green line, it's a little easier to compute invariance. You get better topological properties. Not that you can't compute down below the line, but the invariance that you compute, the topological features that you find, like the sort computed by Perseus or whatnot, are a little easier and a little bit better tied to the topology up here. We'll see some of that as we go on. Okay. So now the details. Now I'm going to be very precise about things, give you some actual mathematical definitions, and we can see exactly some good examples. So what is an abstract simplicial complex? We start out with a set of vertices. I said that before. And then you start looking at collections of subsets of vertices. And there's a condition that says that if I've got one subset, and I've got a subset of that thing that's in there, say this in a quick way, it's a collection of subsets closed under the operation of taking subsets. Collection of subsets closed under the operation of taking subsets. If you don't have that property, then you just have a hypergraph. The elements of this sort of thing are called simplices. So simplices are subsets of vertices. A maximal simplex is sometimes called either a facet or a toplex, depending on who you're talking to. Some people use both. Dimension 0 are vertices. Dimension 1 are edges. How do I measure dimension? Well, I take a look at the length of that subset, and I subtract 1. So this is 0, 1, 2, 3, 4, 5, up to n. That has n plus 1 elements. That is dimension n. So edges are pairs. Vertices are singletons, etc. Okay, so let me give you some good examples of these sort of things to fix in your mind. So one of these favorite databases out there for people in social networks is the Co-Authorship Networks. I didn't pull down this as a data set, but Co-Authorship are good examples of simplicial complex. In this case here, the vertices are authors. So for instance, you might have one author here, another author over here, another author over 2, 3, author 4, and let's put one more here, author 5. And the way this and this paper is co-authored by one and two. And perhaps these two authors have written a paper together. These guys have written a paper together. And if I have three authors that have written a paper together, common in the sciences, less so in the mathematics, then this paper is jointly authored by three authors. So dimension in this case is a proxy for how collaborative, in some sense, the authors are. High dimension means that you have papers with lots of co-authors. Low dimension means that you have papers that are not being co-authored by lots of people. You can look at things that are kind of like graph degree. This author, you can look at his degree and say, yes, this guy wrote papers with 1, 2, 3, 4 other authors. However, it might be useful to think about this with the context of the simplex. And this is why this is very useful, because although this particular author wrote a paper with 2 other authors, and therefore his degree is at least 2 from these 2, it's really the same paper. So it would be quite useful to glue these pieces together. And that's what that simplex is doing. It's saying that, sure, he's got 4 co-authors, but he's only written 3 papers. So it's important to make use of that higher dimensional structure so that you can get a better picture of what's going on. Okay, now we'll see as we go on some other kinds of complexes as well. So there's a complex where, I could rewrite this, where these vertices are telling me wireless access points. And then these are connections between those wireless access points. And the presence of a 2-dimensional simplex says that I've got these 3 channels, or the channels associated with these 3 nodes intersect in some fashion. So in particular, what it means is that only one of these 3 nodes can be communicating at any given time. So it can manage the size of channels and channel capacity. Okay, so very cool. Now, let's try to write this down in this mathematical formalism. So what is it going to have? It's a set of, what are the vertices? The vertices here are authors. Author 1, 2, 3, 4, and 5. So the set of vertices, I'll just say 1, 2, 3, 4, and 5. Now, what does the simplicial complex look like? So I'll call the simplicial complex X. It's a set of subsets of this thing. And so what are they? Well, there's an edge, 1, 2. There's another edge, 1, 3. There's another edge, 2, 3. There's another edge, 2, 5. One that's 3, 5. One that's 3, 4. And then there's 2, 3, 5. Now I got to ask, did I get everything? No. What am I missing?
1, 2.
Yeah, all the singletons. That's right. So all the singletons need to be in here too. 1, 2, 3, 4, 5. Did I get everything? Missing one more. The empty set. Yeah, missing the empty set as well. The empty set is always in there. Not necessarily useful to notate as such because it's always in there, but it's always in there from a mathematical standpoint. Okay.
So what is X again?
So what is X? X is the simplicial complex. That's this thing here. This whole thing is what I'm calling X.
Right. So is it related? Let me think. Is that a
Yeah, so,
So you're saying, well, there are some papers published with
Right.
none of these on them. That
Mhm.
yeah, that's in essence what
I'm
I'm
sorry,
saying.
I didn't hear it, what was he?
Yeah, so what he's asking about is he's saying these are essentially listing all the publications and all the sub-publications. But the top dimensional ones, the maximal faces, the toplexes, are actual publications.
Right.
And you have one as
Yep.
being in there.
Right.
Does that mean that author one had a single author publication?
Okay, no, because it is not a top dimensional simplex.
Think of these as collections of
Right.
authorship.
Yeah, think of the,
Potential authorship?
No, actual authorship.
Actual
These are-
authorship.
These are groups of authors
Right.
that wrote together.
wrote
including
something.
by themselves.
that wrote something. So if you see just one alone, that means author one did write something.
Oh, okay.
Yeah.
Because of that, can the edges of the simplexes have weights? You know how many pages?
Yes, that's a very good question. You could weight them by amount, and then we're starting to add additional data to this data structure. Not an abstract simplicial complex, an abstract simplicial complex with additional data. Now, to your point, you may also wish to actually have a simplex for each publication as well. That's also possible. That's not an abstract simplicial complex. It's an object called a delta complex, which we'll talk about a little bit. Yeah.
So the fact that author 2 and author 3 have an edge between them is just trivially comes from the fact that
Yes.
2,
3 and 5 wrote a paper together. That's absolutely right.
It doesn't mean that 2 and 3
Alone wrote a
alone
paper.
wrote a
Yes, you're absolutely right. And
It's the toplexes that matter. The toplexes are the papers.
the toplexes are the
If
papers.
you're not a toplex, you're not a paper.
And there's, right, and so the line author 1, author 2 is a paper.
Is an actual paper.
But it's also a toplex.
Because it is not included in any higher dimensional simplex. That's right. So this is, but all of these kind of questions bring up the ways that we ought to enrich this data structure. And there are many different ways that we ought to enrich this data structure to represent the information we'd like it to hold. So we can talk about multiplicity of edges, we can talk about weighting of edges, and we can talk about whether or not this distinguished edge here, or this edge on its own, is an actual paper. Maybe additionally 2 and 3 wrote a separate paper. We don't know that from this representation. This representation is not rich enough to tell us that. So it's important to say, okay, this is the starting point, and this is why we're building additional structure on top of it. Okay, so talked about flag complexes. So what is a flag complex? It is exactly as I said before. That was the precise definition. You take your abstract simplicial complex as a graph, or not, look at all the cliques, and make them faces. So take all the cliques, make them faces. So in particular, if I take this simplicial complex and ask for it to be a flag complex, this one gets added. So this is new in the flag complex. And as you can see, the flag complex can potentially destroy useful information. You do need to be aware of that. Sometimes it's useful, and from a topological standpoint, sometimes it's not. In fact, what you might say is, if I look at this co-authorship network, and I look at the difference between the complex that I've built here and the flag complex, these are potential collaborations. Maybe it's the case that author 1, 2, and 3 ought to write a paper together. Now, maybe they don't get along. Yeah, but it's giving you that kind of information. Okay, so flag complexes are often better choices than graphs because you've got this additional high-dimensional data, but sometimes not. So it's important to be aware of what they do. Okay, now, so what is topology? Well, okay, topology is some sense, it's a way to describe neighborhoods of synthesis. This is really good for when I'm telling you about whether a piece of data is valid. So if I'm looking at the paper, or the paper is written by author 3, they're really relevant to author 3 and his collaborators. And author 2 and her collaborators, maybe there are some papers in common, as this suggests, and then we actually would like to know which papers. So we need to know about neighborhoods. So topology is really about neighborhoods and specifying neighborhoods in a precise fashion. Now, in an abstract simplicial complex or a hypergraph, you can write this down very nicely. And we'll do that. There's a very natural topology called the Alexandrov Topology, which I'll tell you about. And fortunately, it's kind of easy to work with computationally. And under the right circumstances, this being one of them, you can translate an Alexandrov topology into an abstract simplicial and that's very handy. Okay. So now, what is a topology? Now, this is perhaps the most abstract definition in the whole tutorial, and one that you can spend an entire semester course on. We're not doing that now, but we'll sort of highlight some of these features. So what is a topology? It's a system of neighborhoods. It tells me what's nearby what. And the idea is I start out again with a set, and I'm going to apply a topology to it. So what is a topology on a set? It's a collection of neighborhoods. This T here is going to be a collection of neighborhoods. It's a collection of subsets of my set of points. And that satisfies a bunch of axioms we can walk through in a moment. But the important thing to keep in mind when translating between topology and abstract simplicial complex is, as far as the topology is concerned, the points are not just the vertices. It's also all of the other simplices. So all of the simplices are in play as far as the topology is concerned. Okay, so now let's walk through the axioms. So first of all, the empty set is in there. It's possible to have a neighborhood that's really boring. Doesn't have any information. The other thing is that another possibility for an open neighborhood is the whole thing. Everything can be an open neighborhood, okay? And then I need stuff in between. And the stuff in between allow me to manipulate stuff. I can intersect, and I can union. Now, for those who are mathematically interested in these sort of things, you notice I've worded intersection and union a little differently. I've worded the intersection in a way that it precludes taking an infinite number of intersections. You can take a pair, and if I take a pair and intersect another one, that gives me 3, and I can intersect any finite number of them, but I can't keep going. I can't have an infinite number of intersections. On the other hand, I'm allowed to take any unions at all. This turns out to be very handy when you and for the most part, we'll ignore it. So the point of the matter is, it's a set of, sort of succinctly, it's a set of subsets that are closed under intersection. It's basically what a topology is. Not exactly because of that finiteness concern with the intersection. It's basically what it is. If I pair up the topology with my set, we call that a topological space. This is a super, super, super general thing. So let me give you some examples, because otherwise this is floating off into mathematical abstraction is probably unhelpful. Actually, I'll say it's definitely unhelpful. So let me give you some examples of topological spaces. Now, being a mathematician, I'm going to first off give you the silliest one. So if I have a set X, so start with set X, start with the set X, here's one topology that always exists. It's called the discrete topology. The discrete topology is, all I'm going to do is I'm going to ask for the set of all subsets. Sets of X. Well, let's see, is the empty set in the set of all subsets? Yes. The whole thing in there? Yes. Any intersection? Well, it included everything. So the other two axioms are trivial. This is kind of boring. This set here represents, the intuition here is all points are far from one another. The name discrete is suggestive. It says that everything is a discrete space. Kind of boring. On the other hand, there's the opposite. There's the indiscrete topology. Fun name. And the only thing it is it's the empty set and the whole thing. Yeah, let's see. First two axioms are satisfied more or less obviously. If I take the intersection of the empty set with the whole set, what do I get? Get the empty set? Sure. Union? Yep, also trivial. So, also kind of a boring topology. This is saying all points are, well, basically in one big mess. That's really, everything is stuck to everything else.
It's really easy to work with.
It's really easy to work with, yes, but it has no structure, no internal structure at all. And there are intermediates as well, various intermediates. This one is a favorite counterexample. This is a favorite counterexample that I love to give to students. If I've got some subset, which is a proper subset of X, then this is a topology. Why? Well, if I take the intersection of A, this subset of X, proper subset, with the whole thing, I get A. That's in there. Intersection there, I get the empty set, and union goes the other way. Also kind of boring. This is saying that A is kind of glommed together, and there are points in A, and they're stuck together, and points away from A, and they're kind of also on their own. So that's sort of weird, and not necessarily that helpful. But let me give you one that's a little more reasonable. So another example is the real line with all open intervals and the unions thereof. So this too is a topology. This is called the usual topology. So let's see. Is the empty set in there? Well, yeah, I can take an interval that goes from X to X. That's an empty set in the case of the open intervals, because the open interval from a point to itself doesn't include that point. So that's an empty set. Sure, that's in there. The whole interval from minus infinity to plus infinity, that's in there too. Okay, good. What about intersections? If I take two open sets, open intervals, and I intersect them together, do I have an open interval? Yeah. If I take their union, do I have? Yep, that works too. So that this is what people call the usual topology, and this is the model for when things work correctly. So this is a good topology model for when things work correctly. Now there are lots of other topologies out there as well that are adapted to simplicial complexes. So that's what I want to talk about next. The way you do that is you take this simplicial complex, like one we had up on the board a moment ago, and take a look at what's called the star over a given simplex. Here's the star over this vertex. It's all of the simplices, all of the sets that contain it. So this edge contains this as a subset. This two-dimensional simplex contains that as a subset. This one also. Does V3 singleton contain V1 singleton? No. So this is not in the star. What about V3, V4? Does that contain V1? No, so that's not in the star. So the star is sort of a prototypical open neighborhood. Let me show you another star. Here's the star over V1, V2. Is V1, does that contain this? No, because this is smaller than this one. So that point is not in the star over this. But this one does contain. So in particular, what the star is doing is it's capturing all the higher dimensional simplices that you're attached to in some fashion. This gives you sort of prototypical open neighborhoods. If you take all the unions of the stars over various simplices, you end up with a topology. That's called the Alexandrov topology for this particular simplicial complex. And it's really the right one to use for data integration. Works for abstract simplicial complexes, just as I showed you. Works for hypergraphs as well. Works for any preorder, in fact. You can build this. That's kind of handy. And so this is the topology that really represents things nicely. Why does that work? Well, let's take a step back and look at this. So what I'm doing is I'm asking for, let's look at my axioms. I want to know about the intersection of, say, this guy and this guy. What's the intersection of these two guys? Just this one. Is that in my set? Well, yeah, by construction. What about the union? Of course, the union's that, again, in my construction. You can walk through all of these various things to find out, yep, this works. Of course, the finiteness is helpful for avoiding the subtleties of the axioms, but that basically boils down to it. This Alexandrov topology is very handy, and it allows me to generalize things a little bit. So, addressing the question about multiple papers. If I have multiple papers between two authors, here's two authors and they've got multiple papers, you could weight them numerically, but perhaps a more topological and better approach is to put multiple edges between them. Then what you end up getting is you end up getting various different kinds of stars. So this is a star over this edge. This is a star over this vertex. This is a star over this edge. Remember, all the edges are individually thought of as points. So this gives me a way to represent multigraphs topologically. This gives me a way to represent multi-simplicial complexes in a nice way. So this ends up posing no computational problems to do this. And lots of people use multigraphs. But this allows you to talk about multi-hypergraphs and other such things as well in a reasonable, consistent fashion that then ties to the topology I mean, by construction, because it is a topology, that's Alexandrov topology, and it will tie to this construction of sheaves I'll give you later in the next lecture. So what about if we don't even want hypergraphs? We want to start talking about attachments. That turns out to be really the next sort of thing we want to look at, is that really there's a partial order. Starting from vertices, I can link from vertex to edges to say that vertices glue to edges. There are subsets of edges. This partial order turns out to be really very useful. It's not very topological in a sense, but it is. And this turns out to be important. Yeah?
So in some of your examples, you have things labeled. You don't have labels on
Sure.
there. So I guess each point would have a label, and then each...
This has a label, this has a label, this has a label, this has a label. The reason why I haven't labeled them is because everything's got a label, and you can pick whatever you like. Yep, that's right. So the important point here is that if I know that this vertex attaches to these two edges, that's what's important. This is going to be the places where I'm going to want to translate and transform information that's going to be stored on these various vertices and other simplices. Okay, cool. So if I start with the topology now, that's great. So how do I start with the topology and work with things? If I start out with a physical region from sensors, how do I turn that into a topological space such as I've been telling you? How do I do that? But if I start with a topology, that's easy, but how do I start from physical data? Well, it's usually good practice to assert that my sensors have open sets as sensing regions. Now, sometimes they come from the usual topology, sometimes they don't. But let's go back to this example that we saw in the first lecture, where each of the sensors have a certain sensing footprint. Those sensing footprints should be thought of as open sets. Now, what does that mean? That means that then I have these various open sets sitting here, and what I have to do, if it's a topology, I have to be able to intersect and union them. The fact that I have non-trivial intersections, non-empty intersections between these two open sets and these two open sets and these three sets, that turns out to be really very useful, and that's what gives rise to the topology. This is now the topology that we're using. We're using the Alexandrov topology on this thing, which says I've got an open set associated to this guy, an open set associated to this guy. They've got an intersection, which is yet another open set, and they even have a three-way mutual intersection, which is yet another open set, as well as all the various unions. Yeah?
Oh, what does it mean? I mean, if you have a set of data points,
Yep.
what does it mean that that's an open set?
Okay. So over here, I'm saying it's an open set of, say, the Euclidean plane. The real plane. The plane, or this map. It's an open set, as in it is really looks just like what you would think from calculus as an open set. That turns out to be the right topology. Now, what I'm doing, though, when I go from here to here, is I'm only remembering a certain number of open sets. The one open set that sits over in fact, specifically, this blob, that particular open set. That I'm thinking of as being this particular open set, just sitting here.
Oh, so then,
So there's a direct correspondence.
in physical reality,
Physical reality.
there is like an uncertainty,
Yeah.
uncertain area.
Well, or either uncertain area or even an area of regard.
Of what the
That's
sensor
right.
can measure.
That's why it's open.
Okay.
That's why
But
it's
if
open.
it were a sensor in a room,
Maybe it does have
then
boundaries.
there would be a wall.
Indeed. And actually, you know, this is one of the things that people in topology have thought about a lot. You know, I can make a topology that looks like this, which is sort of a very strange topology that includes boundaries. So in a room, that boundary is not necessarily an obstruction to it being an open set in an appropriate topology. It's sort of a weird thing, but it turns out to be okay. The point is that relationship structure between the data sources, not precisely what do they look like in physical space. Now, to make that very precise, this particular construction comes from something. It's called the nerve. The nerve, here's the precise definition of the nerve. It's given a topology, collection of open sets, there's a way to turn that into an abstract simplicial complex. So I told you a way to go from an abstract simplicial complex to a topology, the Alexandrov construction. This is the nerve construction. It goes the other way. Given a bunch of open sets, here's how to turn it into an abstract simplicial complex. So it's the reverse. And under the right condition, the Leray theorem, they match up. They give you the same information. So essentially what you do is you say every open set is a vertex. Every prototypical open set is a vertex. Every time that I have a non-empty intersection, then I put in an edge. Every time I have a three-way intersection, I put in a two-dimensional face and up the dimensional chain. So that's pretty handy. That gives me, in fact, that is precisely what gave me the construction on the previous slide. Okay, so this gives me a very strong link up for how I should build my topological spaces. Start with that topological space if you've got it, and you can turn it into a nerve if you like it, in the case of the physical centers. Or you might start with the data giving you the topological spaces, and it gives you a graph, or like a co-authorship network, it gives you a simplicial complex. You can turn that into a topology. Okay, and so next up, lunch. Lunch is here, so that's very nice. And then the next lecture, which starts at 1:30, we will define what it is that I mean by sheaf, precisely. Okay, there's some references.